easy. All right. We start off by looking for eigenvalues, and then we find the eigenvectors. So let's do that in that order. So e-values, we start off with a minus lambda I, the determinant of that, and we know that it's just going to be subtract lambda from the diagonals, 1 minus lambda, 2, 2, 1 minus lambda. Find a characteristic polynomial, so the determinant of this is 1 minus lambda quantity squared minus 2 times 2 is 4. And then we have 1 minus 2 lambda plus lambda squared minus 4. And then I think that's lambda minus 2 lambda minus 3. Is that correct? This should be easily factorable. Lambda minus 3 lambda plus 1. And so we got lambda is equal to 3 and lambda is equal to 1. So we have two distinct eigenvalues, and this is what? Negative 1. Thanks. We have two distinct eigenvalues, so we're not going to have any issues about multiplicity here. So this should be pretty easy. Get. And each of these should have one eigenvector associated with it. And let's go ahead and find that. So I'm looking at the eigenspace for, let's try the eigenvector for negative 1 first. So I'm going to denote that as E sub 1. That's what I'm looking for, your eigenspace. And you'll find, I was going to say one or more vectors, but in this case you should just find one vector. All right, so we're going to say lambda is equal to negative 1, and then put it into this A minus lambda I, and then we want to find the null space of it, so we're going to make that matrix and set it equal to 0, or the system set equal to 0. So I have 1 minus negative 1, so that's going to be a 2. The other one's 2. Oh, this is going to be a 2, 2, 2, 2. So row reduce, not equals, but row reduce. I guess it doesn't matter if I put 1, 1 or 2, 2, but it'll wipe out the whole bottom, which is what we would expect to happen, and then we would let one of the variables, the last variable, be equal to some free variable parameter t, and then we can solve for x. 2x plus 2y is equal to 0. So replace y with t and then divide by 2, so y is equal to, should be negative t, right? So if we write this by factoring out a t, your x is going to have a negative 1, and then your y is going to be just positive 1, and that is your first eigenvector. That's the eigenvector associated with negative 1, and we'll do the same thing for 3. All right, so put 3 in there. We're going to get a negative 2, 2, 2, negative 2. So it looks almost the same. Again, not equals. Negative 2, 2, 0, 0. I think negative, or just adding the first and second rows will give you this. And then your free variable again is y. And then your x is going to be, this time, positive t, I think, right? So we have xy is equal to t, and then you get a 1, 1. So if you look at these two vectors should be linearly independent according to those theorems. If you put those two vectors together, they should span all of R2, because they're two-dimensional vectors in R2 and they're linearly independent. They should be able to span all of R2. And then they would make up your P matrix. So it looks like our P matrix, well, it depends on the order of our D matrix. It has to correspond with our D matrix. So I usually like to put the lesser number first, and then, but it doesn't matter as long as you're consistent. So I'll put -1 first in the diagonal, and then 3 second. And that makes your P start with a -1 eigenvector for -1. That's -1, 1. And then the eigenvector for 3 is 1, 1. And then if you want, we don't need to, but if you want, we can find the P inverse. I'll just remember the formula for the inverse of the 2 by 2. It's 1 over the determinant. So this is -1 minus 1, that's -2. So 1 over -2. And then switch the diagonals. And then negative the wings. So this is your inverse. Do you guys remember doing the inverse like that? You should be comfortable with quickly finding the inverse of a 2 by 2 matrix. And we don't need to check this. I'm not going to check it, but if I just put this together and multiply it out, I'm going to get -1/2, +1/2, +1/2. That's your P inverse. Your A matrix, our original A matrix, is 1, 2, 2, 1. Then your P matrix is -1, 1, 1, 1. And if you do this calculation on the left-hand side, you should get your diagonalized matrix on your right-hand side. Okay? Now, yeah. Yes, you should get the same number. And then if you count multiplicity, you should get exactly the same number. But possibly you can get less. Yeah, so if you had switched it the other way, it still should be okay. If you say start with a 3 and -1 in the diagonals, then your corresponding P matrix for that would be the matrix, the same matrix, except the columns are switched. So you could have done it that way. It should still give you the same result if you did this checking to make sure that it's correct. Okay? All right. So there's a lot of interesting applications for this that we're not going to do. But there's one in this particular section that they do talk about, and that's taking a matrix to a power. You know, I'm not talking about to the 3rd or 4th power. I'm talking about to like the 15th or the 2000th power or something ridiculous like that. So if for any reason you need to do that to your matrix, you need to take it to a really high power, diagonalizing a matrix would really be helpful. Did we do that in class last time? Taking it to a power? I don't think so. I think I was doing something and sketching it out on my computer, and maybe I just thought I was in class doing it. In reality, I was somewhere else. In Hawaii. All right, let's try to do one of those. Before we do it, let's get the idea of raising a matrix to a power. So a to the k. What does that mean? Well, that means you're going to multiply your matrix k times, right? That's what it means. What was I going to say about it? Oh, so if your matrix is diagonalizable, then your A diagonalizable means that you can write your matrix A like this with a matrix D and another matrix P. And so if remember the reflective, remember when we're talking about a matrix being similar to another matrix, then there's this reflective property, which means A similar to A, and then no, that's reflective. Yeah, the symmetric property says if A is similar to D, then D is similar to A. And the quick proof for that is that I just want to write this with an A by itself and a D with those two matrices around it. So if I take the inverse, let me write it. Let me rewrite it like this, and then give this a little bit more space. So if I take D and I multiply this green, and I multiply this by P on one side, and then I'll multiply this by P inverse on the other side. Can't decide. Then I'll just have A on one side, and this is P, D, P inverse, right? And to make this really, really formal, the inverse has to come first, and so I can just write P as P inverse D, P inverse, and then it might help if I put parentheses around here. So the P inverse in parentheses is another matrix that's invertible. I could pretend that that's equal to Q or something. So now I have that symmetry saying if one matrix is similar to another, then that other matrix is similar to the original matrix. Okay? All right, so now that we're able to take that idea and we take A and raise it to the kth power, what does that mean? That means A to the K is equal to this whole thing, Q inverse DQ raised to the K power. And what does D inverse or Q inverse DQ mean? Raised to the K power, that means you take Q inverse DQ, multiply it with itself, okay, I should stop sometime. K times. Okay. So, how does that make things easier? Well, it turns out that we know that it's matrix multiplication is not commutative, but it is associative. So that means I can regroup. And what I'm going to do is, well, you know, all these Q's and Q inverses are right next to each other. I can regroup to put those two together a bunch of times. And so they would just equal to the identity matrix and more or less disappear. So I'm not going to completely get rid of them. I think I still have one Q left on one side, the inverse. And then I have D a bunch of times. Oh, why don't I just call it D to the K power? and then one final q at the very end. Wait, what's D inverse again, or Q inverse? Q inverse was P, wasn't it? So Q inverse is P. So this is just P, the original P matrix, D to the K times P inverse. So it's a big deal. If you have a diagonal matrix, raise it to the K power. Did we do this? Did we talk about a diagonal matrix raised to a power? It turns out that it's just each of those diagonals raised to the K power. So that really makes this nice and handy. So I can easily take a diagonal to any power I want, and then if I want to find a to the K power, I'll just diagonalize it, if it's diagonalizable, and then raise the diagonals to the K power, and then just multiply by P and P inverse. It could be a lot easier than multiplying your matrix by itself a bunch of times. So, all right. So that's a neat little property for inverses, and it's a good simple application for diagonalized matrices. So let's do some of these problems. You guys still copying? Let's do number 15. There's no 15. Let's do number 16. All right. So we can easily take this to the fifth power. Well, I don't know how easily, but instead of doing it that way, let's do it using diagonalized matrices. Let's see how much easier it is. And then we'll check our answer using something like Mathematica to take this to the fifth power. All right, let's focus on the matrix A itself, just -5, 8, -4, and 7. And then find the eigenvalues, and then eigenvectors, and then make the matrices, and then let's take it to the fifth power. All right. Let's start with E values. And for this, we're going to start off with -5 minus lambda 8 -4 minus lambda 7. The determinant of that is 7 times -5 minus lambda minus 8 times -4 minus lambda. There's a lot of negative signs here. Try to get rid of all that. -30. Oh, I did this wrong, didn't I? Yeah, I thought something was kind of weird. Sorry about that. I was in Hawaii for a minute there. Let's try that again. Characteristic polynomial, -5 minus lambda times 7 minus lambda minus 32. So -35 negative, positive 5, negative 7, negative 2, I hope, plus lambda squared plus 32. So lambda squared minus 2 lambda minus 3. Minus 3. So this is very close to the other one we had. I think lambda is equal to, we'll have a minus 3, so that's positive 3 and negative 1. I better factor it first. Lambda minus 3, lambda plus 1. Uh-oh. Is that right? Did I do the other one wrong? Oh, it's the same thing. It's the same thing. I thought it was a plus. I thought the other one was a plus, and now we're getting the same roots, and that would have been bad. So we have the same roots as last time. Let's check our Eigen Vectors. So the Eigenvector for lambda is equal to negative 1. We'll start off with that. You want to row reduce your a minus lambda I when lambda is equal to negative 1. So negative 5 plus 1 is negative 4. And then 7 minus negative 1. 7 plus 1 is 8. Oh, there you go. Disappears. So you can make the whole bottom equal to 0. And I can factor out, or whatever, take out a 4. So minus 1, 2, 0, 0. And then this gives me an Eigenvector. So if I let my y equal to a free variable, minus x plus 2y is equal to 0. And then x is equal to, bring that over to the other side. This remains positive, 2t. So xy is equal to t, and then the 2 for the first one and the 1 for the second one. So I got one eigenvector. I got the eigenvector, the eigenvector for negative 1. And now let's check for negative 3, or not negative 3, positive 3. Again, we start off with our a minus lambda I. Lambda is equal to 3, so negative 5 minus 3 is negative 8. And this is 8. This is negative 4. And 7 minus 3 is 4. All right, so do what you need to do to reduce this. I'm going to go with negative 1, comma 1, or negative 1, 1, and 0, 0. So another free variable for y, and then your x, negative x plus y is equal to 0, so x is equal to positive y, or positive t. So this is going to be 1, 1. Okay? And by inspection, quick check, 2, 1 is linearly independent from 1, 1. So you make up your eigen basis for all your eigenspaces. And there will be your columns for your matrix P. Good so far? So stuff that we've been doing. Now let's make our matrix P and D. So P, let's write D first. So D is equal to you have the two eigenvalues, and it doesn't matter which one goes first. I like putting the lesser one first, -1 and 3. And then your P matrix is the associated eigenvector for -1 is 2, 1. And then the other eigenvector is 1, 1. Okay, and the inverse is 1 over the determinant. The determinant is 2 minus 1. That's just 1, right? 1, and then switch the diagonals, negative the wings. So that's your inverse matrix for P. All right. So now our magic formula is saying a to the k is equal to not P inverse, but the original P times d to the k times P inverse. And remember, when you take a diagonal matrix to a power, all you're doing is raising the diagonal matrix to a power. So -5, 8 minus 4, 7 to the 5th power is equal to your P matrix, 2, 1, 1, 1, times your D matrix, -1, 3, raised to the 5th power, and that, remember, is just taking the diagonals to the 5th power. And then finish it off with the inverse, 1, -1, -1, 2. So I think -1 to the 5th power is -1. I just have to figure out what 3 to the 5th power is. It's 3, 9, 27, 81, 243, 243. So 2, 1, 1, 1, -1, 0, 0, 243, 1, -1, -1, 2. And then just multiply. So I get 2, that's -2. I'll do the first two first. -2, 0, 0, 243, -1, and 243. And then now I'm going to multiply the inverse. So this is -2 minus 243. What is that? -245. -2, +2, plus 2 times 243. That's 486. 46 plus 2, 490. Right? Did I do that right? Yeah. Eraser was okay. So what should it be? 488. Okay, and then -1, -243. That would be -244, and +1 plus 2 plus 486, 487, 487. All right, that was not as easy as I thought. We should check with Mathematica here. So our matrix A is, what is it? -5, 8. -4, 7. And then we want A that right? Yep, looks good. All right, so the fifth power might not be so bad, but if you take a look at one of the other questions here, it's raising it to like the 2002 power, or raising it to the kth power and stuff like that. So I think that's a little bit more challenging, more interesting. Should we do number 21 or 23 or 22 or 20? 23 or 22? 23. Oh, there's another one with a K that I wanted to do earlier. I'll do that. All right, so this is a 3 by 3. We should try to look for those. Should we look for the eigenvalues and eigenvectors by hand? Or can I use Mathematica since I have it? Use Mathematica? Well, the thing is, can I trust that you guys know how to do this by hand? Eigenvalues and eigenvectors? Yeah? Yeah, okay. So if you just look for, if you Google YouTube or go to YouTube and just say eigenvalues and eigenvectors, and they'll walk through the process. This is one of those basic operations in linear algebra. All right, let's get this going here. 1, 1, 0. 2 minus 2, 2. 0, 1, 1. Okay. We want the Eigen System. So the Eigen System allows me to get the eigenvalues and the eigenvectors all together. And so here are my eigenvalues, negative 3, 2, 1. And for each of these corresponding, the first, second, and third slots are going to be the eigenvectors. So let me just copy that. So I think if you go to Wolfram, you can find the eigenvalues and eigenvectors. I'm not sure how to do it in MATLAB, but it's a matrix program, so I'm sure if you just type eigenvalues, you'll find something. All right, so we have 3 eigenvalues and the eigenvectors corresponding. So I can immediately write my D vector or D matrix. D is equal to negative 3, 2, 1. It doesn't look like they're going according to how I normally write it, right? I go from lesser to greater, so it should have been negative 3, 1, 2. But again, it doesn't matter as long as you're consistent. So the first one is the eigenvalue for negative 3. The second one is the eigenvalue for 2. And then the last one is the eigenvalue for 1. So if we just put that in that specific order, our P matrix is going to be, for negative 3, it'll be 1, negative 4, 1. Remember, I have to write these as column vectors for my matrix, or columns for my matrix. The middle one is 2, so I have a 1, 1, 1. And then the last one is 1, so I have a negative 1, 0, 1. And then we would want the inverse of this, which we can use Mathematica again for that. So let's go ahead and find the inverse of that P matrix. Pad left. It's pad left. So I'm going to type in my P matrix. And then I'll find the inverse of that. So we have a denominator of 1/10 for them. It's a little sloppy, but this is the inverse matrix. All right, so let's find this a to the k is equal to P, now the D matrix, and then P inverse. So your P matrix is 1, 1, negative 1, negative 4, 1, 0, 1, 1, 1. I have negative 3 raised to the k power, and since I don't know what k is, I just have to leave it like that. I have 2 raised to the k power, and 1 raised to the k power is just 1. And then I have my P inverse. I'll just put P inverse here for now. So the idea is we want to multiply this out. So we can multiply this out. Can we? All right. So the first one, multiplying out with a diagonal matrix isn't bad. When we start multiplying it with this other matrix, then it's going to get really messy. But for now, let's just multiply this out. We got 1 times negative 3 to the k. I should put parentheses around this negative 3 to the k just so it's clear that that's being raised to the kth power. So if it's an even power, it becomes positive. The second one is 2 to the k, and then negative 1. Negative 4 times negative 3 to the k, 2 to the k again, and 0. And then the last one, negative 3 to the k, 2 to the k, and 1. And then now let's multiply it by, well, I don't know if I want to do this. Well, let's see what we can do. Now this is going to be a bigger matrix, and it's going to be a lot messier. And it'll have these symbols that you can't turn into numbers because there's a k there that's unknown. So let's just go through the first line. Maybe I'll stop, or maybe I'll keep going. 1/10 times negative 3 to the k. Row, I'm not done with this yet. Plus 2/5 times 2 to the k. Row, and then plus 1/2. So this is just the first element of my 3 by 3 matrix. let's see, my second element is going to be the first row and the second column. So that would be a negative 1/5, negative 3 to the k, positive, so plus 1/5 times 2 to the k, and then 0. So that's my second element. And then let me just do one more so I can finish the first row. First row, last column. So that's a 1/10 again. Negative 3 to the k. This is 2/5 positive times 2 to the k. And then negative 1 and 1/2 is negative 1/2. So that's my first row. Yeah. Yeah, just treat k as a number and then nothing else you could do about that. And since we don't know what it is, we can't simplify this any more than what we did before. So can I just put boxes here and say you figure it out? Okay. I mean, I could get the answer by punching in Mathematica also, but you get the picture, you get the idea. All right. So this is a neat little application. It's easier, right? Easier. Well, maybe it's easier. I want to backtrack a little bit, and there's a few problems that involve this unknown k, mystery k problem thing again, where it involves us trying to find out some information about whether something's diagonalizable or something is similar or something like that. I forgot what it was. But it was in my notes, and I meant to do a problem last time. Here you go. It says find all real values of k for which a is diagonalizable. So let's do one or two of these. Let's start off with 24. I wanted to capture the instructions here. So k is some unknown value. You got to treat k differently from what we saw k in the previous problem, or how we saw k in the previous problem. But let's see how we can approach this. It says find all real values of k for which a is diagonalizable. And remember, for it to be diagonalizable, we have to find the eigenvalues, and we have to find two linearly independent eigenvectors that would work. So let's start off by doing the process for finding the eigenvalues. So we have 1 minus lambda, 1, 0, and k minus lambda. And k is something that we have to look for. The determinant of this is 1 minus lambda times k minus lambda minus, oh, that's 0. Okay. So I think that's it, 1 and k, right? If we set this equal to 0, it's already factored, so lambda is equal to 1 and lambda is equal to k are your two eigenvalues. So let's take a look at the eigenvector for 1. So when lambda is equal to 1, I have 0, 1, 0, and then k minus 1. So let's see. How can this work? Do we have a free variable? Well, first of all, we have to make sure that we get a row of zeros, right? And we're looking for the null space. If the bottom is not equal to 0, then we can we're not going to be able to do this. So and then if the whole bottom, if you don't have any 0 rows, that means the only vector that would work in the null space is a 0 vector, which is not good for us because we're looking for linearly independent values. So can K be anything? Can K be 0, 1, 2, 5, 7? So if K is equal to 1, then the whole bottom is 0, and then you're kind of done with that. So K can be 1. Can K be equal to 2? Yeah. So at this point, K can be anything, right? Because if we multiply the first row by negative K plus 1, or K minus 1, first row added to the second row, you're pretty much guaranteed to get rid of that row, and then now you can build your matrix. So it looks like Y is going to be 0, and then X is your free variable in this case. So it looks like your Eigen Vector, your E vector, X, Y is going to be T, and then 1, 0. So your Eigen Vector is going to be 1, 0 in this case. Right? So it's the 0 on the bottom, and you start setting this up. You say Y is equal to, because this whole thing is supposed to be equal to 0, right? So the whole bottom 0, and this is Y is equal to 0, so that you're kind of left with, what am I going to do with my X? Usually when you don't know what to do with something, you just say, oh, it's a free variable. So it's a free variable, X is your free variable. Usually, you know, Y is our free variable, or Z, and then you build up from the top. But in this case, X is our free variable. So the eigenvector for 1 is the vector 1, 0. Yeah?
So does that mean that T parameterizes the subspace?
Yes. Yeah. And if you have 2 parameters, like if you have 2 free variables, then your T and your S parameterize a 2-dimensional subspace of R3 or R4 or whatever. Okay, let's go to E sub K. This is now your second eigenvalue. And if lambda was equal to K, you want to find the null space for this matrix. 1 minus K, 1, 0, and this is K minus K. K minus K? 0. Right? Okay. So you got the whole denominator be equal to 0 already, so you might as well just jump and say, let's just let your Y be your free variable. Y is equal to T. And then now you have 1 minus K times X plus Y is equal to 0. So then X is equal to, bring the Y over to the other side, and we might as well call that T, negative T divided by 1 minus K. I guess that's equivalent to saying positive T. Can I put positive T in there? And then switch to K minus 1. Not that, I don't know if it'll make a difference. In any case, your solution for the null space is going to be 1 over K minus 1, and then the second one is just T, so factor the T out and you get that. So this is your Eigen Vector for K. Now the fact that I'm looking at these two, the fact that the second component of the vector is 1 and then the second component of the vector here is 0 means they're going to be linearly independent. And it really just depends on what this first component is for the first one. So I can make this any number I want, except, of course, you can't have 0 in the denominator. So it looks like the only bad thing is 1 over k minus 1. If k is equal to positive 1, then that's not good for our vector. But k can be anything else, right? I don't know what else to say. It's bad. So k is equal to 1 is bad. Anything else good? Any other k is okay. So all real values of k for which a is diagonalizable, we can conclude then a is diagonalizable. If k is not equal to, I was going to put 0 here, if k is not equal to 1. So if you put k is equal to 15, it'll work. If you put k is equal to 0.5, it'll work. So k can be anything as long as it's not equal to 1. Is that okay? Okay, let's, you want to do another one? 3 by 3 matrix, or are we done with this? Yeah? K can be what? In this particular problem, they just want you to look for just real values. But technically, yeah, k can be a complex number, and then weirder things will happen with eigenvalues and eigenvectors when you start talking about complex numbers. But in some cases they could be. But in this particular problem in our class, we'll just stick with real numbers. Yeah?
So when they're talking about diagonal matrices, sometimes they talk about tridiagonal matrices, where there's more than one column entry.
More than one diagonal? Yeah, we won't talk much about that here. There's special types of matrices where the diagonal is filled in with non-zeros and then maybe another set of non-zeros and then 0 everywhere else. Yeah, or they might mention, or it might be down here. This is what I was looking for. Like maybe 3 non-zero diagonals below, and then everything else above is 0. This is kind of like a lower triangular anyways, but there's some special cases where a few of these things are diagonals or non-zero, and everything else is 0. So they often look for that because then the data that holds that information is going to be less than, because if it's a 0, then you don't need to worry about holding a place for that particular value. So yeah, they have these things, but I don't know how helpful these things are for what we're doing. Might be useful for your thing. Okay. Should we do one more? Or what? Let's do one more. Let's do one with the 3 by 3. Of course, it's going to take more than 6 minutes, but see how far we can get. Okay, so there's this, I guess we can consider this an upper triangular matrix. And let's find the eigenvalues. So let's start off by writing, I want the determinant, so I'll use straight bars. 1 minus lambda, 0, k, 0, 1 minus lambda, 0, and everything else. So I have 1 minus lambda to the third power. Oh, what am I doing? I'm just thinking about the 2 by 2. I need to find a determinant of this, so I need to find, I need to expand. So I could expand on the first row. Why don't I expand on the first row? So first row, I have positive, or I'm expanding on the first column. I'm expanding on the first column. So I have positive, negative, positive. And they're all zeros, so not like those signs are going to make a difference, but I should write it down anyways. I got 1 minus lambda, and then I cross that out. And then I find the determinant of this. This 2 by 2 matrix, which is just itself. So it looks like 1 minus lambda cubed, right? So if this is set equal to 0, I have lambda is equal to 1 with, let's call it algebraic multiplicity. Of 3. So notice k didn't play a factor here. I'm looking for this algebraic multiplicity business. But let's see how much it plays into the factor when we start looking for eigenvectors. So I hope to get, I don't think it's going to happen, but let's see, I hope to get 3 vectors for this. Now let's see if we actually get 3 vectors. We get, what do we get? So we'll take this matrix. We want to find a null space when e is equal to 1. So I have 0, 0, k, 0, 1 minus 1 is 0. So the whole thing goes to 0, except for that k. So I can assign, if k is not equal to 0, my y, or my z, I guess that's my third variable, z is equal to 0, and then x and y are free variables. So what's that mean? That means my x, y, z solution is going to be s times 1, 0, 0 plus t times 0, 1, 0. So I have 2 linearly independent eigenvectors. So in the old notation, our E1 is going to be the span of 1, 0, 0 and 0, 1, 0, which makes it a 2-dimensional space. These two are linearly independent. So this has geometric multiplicity. Geometric multiplicity of 2. Unfortunately, for this to be diagonalizable, the algebraic multiplicity has to match with the geometric multiplicity, and it doesn't. Right? So we have a problem. And this happens when we assume that k is not equal to 0. So if k was equal to 0, then you essentially have a zero matrix, which then would allow you to have 3 free variables. So z is a free variable, y is a free variable, and x is a free variable. What should we call it? R. That's the one right before s, right? R. And in which case, I mean, I don't think we have to write this down anymore, but just to make it clear, R100 plus S010 plus T001. So now you have a 3-dimensional eigenspace, and that's the only way you can get this to be diagonalizable, is that if k was equal to 0. So A diagonalizable if k is equal to 0. And if k was equal to 0, if you look at your original matrix, that just means it's identity. And so your eigenvalues are 1, 1, 1. Your eigenvectors are just make up the identity matrix. So, okay. That was a little bit of a dud, but that's how it goes. So k has to equal to 0. Any questions? All right. Next time we're going to start with Chapter 5. I need to give you guys a quiz in this. You guys like the take-home quiz scenario? Better than taking the quiz in class. As if. So I'm going to post a quiz sometime on Friday relating to this diagonalizing business. And then maybe I'll collect that on Wednesday next week, give you a little bit more time. Okay? All right, that's it. See you guys next time.